My name is Sebastian Billaudelle, and I'm also one of the people drawing transistors by hand. I'm trying to continue with the story Gerd has started telling. He talked about the neuron we built for the next generation neuromorphic hardware, and I'm trying to convince you that we can do the same things for more principles in the brain, for example, synapses and synaptic plasticity. So on the right-hand side, you see the current prototype we are building. This is HICAN DLS. HICAN stands for High Input Count Analog Neural Network Chip. And so this chip is a mixed signal neuromorphic hardware. We have these analog circuits doing the emulation of neural components, neurons and synapses. And mixed signal means that we also have a lot of digital components on there. And just to give you a sense of the scale here, this is a prototype. This is really small. You have those tiny wires that we actually place by hand under a microscope going into that chip, and the length of one edge is 1.2 millimeters. So it's really tiny. The biggest part of that chip, of that brown area, is actually not hand-drawn. But it is digital circuits. And most importantly, there's the plasticity processing unit, or PPU, which is a general purpose processor. It's an embedded processor we designed in Heidelberg, and it allows you to implement, like in an actual programming language, plasticity rules, learning rules, which are correlation based. So something like STDP. And now we're coming to the hand-drawn stuff. So that small rectangle marks the boundaries of the ANN core, the analog core. And since it's a prototype, we only have 32 neurons on there, and we have 32 times 32 synapses. And we can just zoom in there a little bit. This is a schematic drawing of the same thing. On the bottom, you see the neurons. And above those neurons, there's the synapse matrix, or synapse array, which is used for input routing. And on the left of that array is, again, an array of synapse drivers. And Mihai told you that those drivers are not important. They actually are important. And for that, I'm going to explain to you how we transmit events from the digital communication backend, which are the arrows on the left, across that array to the neurons. So the synapse drivers create a voltage pulse and send those pulses across the whole array. This voltage pulse is very short. It's about 0 to 4 nanoseconds long. And that is already 1 degree of freedom. We can change the starting and the end point of that pulse. The synapses have a 6-bit SRAM memory in them. And these 6-bit are used to store the weight of the synapse. So that means we have 64 different weights per synapse. And the synapses have a small current source, basically. And this current source is enabled for the duration of the voltage pulse it sees. And the current is proportional to the weight stored in the synapse. So that gives us the second degree of freedom, the amplitude of the pulse. STDP, as controlled by the PPU, modifies the weight of the synapse. And short-term plasticity, which is the topic of my master's thesis and of this talk, is applied by modifying the width of the pulse, which is happening in the synapse driver. But let's take a step back and talk about short-term plasticity. What is short-term plasticity? It's a concept modeling the dynamics of the neurotransmitters at the synaptic cleft, and I think it was first described by Sodix and Markram in the late 90s. And this drawing, or this plot, is from Sodix and Markram, and it's an actual, so it's averaged over multiple traces in vitro. And the basic intuitive idea behind STP is that you have a finite amount of neurotransmitters at the synaptic cleft in the presynaptic neuron. And when you have successive spikes, you will see that the amplitude of the PSPs on the postsynaptic side will decrease because there's not enough neurotransmitters left. If you wait some time, you see a recovery happening. So there's that recovery response by PSP. It's increasing in amplitude again. And we can describe this behavior in simple differential equations. So we are only talking about the top equation now. I is basically proportional to the amplitude of a PSP. And the first term on the right-hand side is the recovery process. It's just an exponential with a time constant tau rec. And the right-hand side, the second part of the right-hand side is a discrete update step, which happens whenever there's an incoming action potential on the presynaptic side. It turns out that there's a very simple circuit which follows exactly the same dynamics, like with a neuron, but this is only for STP. And this simple circuit is really following exactly the same dynamics as those differential equations. Of course, there's more to it because, for example, we can't take a 15 giga-ohm resistor and put it into an ASIC. That is impossible. There's no such thing. So we need to do tricks, and then we distort the model a little bit, and it's quite hard to get an intuition of how this circuit behaves. But there's a thing we can do that is called a transistor level simulation. So we can simulate the circuit we are building in very much detail, and Laura is going to talk about this in more detail. And I have done this for my circuit, and this is how it looks like. So you should see basically no difference except for parameters from the left to the right. The right-hand side is a simulation of the circuit which is going to be in the next prototype, which is actually back in the lab. So if you want to talk about neuromorphic hardware or short-term plasticity or microcircuits, hand-drawing transistors, then I would like to welcome you at the poster session. Thank you.